Chapter 10, Gases. This chapter is interesting in what we discussed earlier. We went through all the various theories, right? Dealing with the quantum theory and then Lewis theory, Vesper, hybridization, MO theory, and now we're coming to gases. Now, what we're going to deal with in this chapter, we're going to talk about characteristics of gases, pressure, the gas laws, the ideal gas equation, and we're going to see application of ideal gas equation and how is applied. What that means, basically, we're going to deal with a little bit of density there, because we're going to correlate density to gas law. And then we are talking about the mixture of gases, partial pressure, kinetic molecular theory, effusion, diffusion. I believe you probably didn't have these last few parts here. And real gases, very much different from ideal gases. We're going to look into that. All right. So what's the difference now? We have different physical state, and we had liquid, solid, and now gases, right? So you understood the liquid, the sense that the liquid had in terms of the intermolecular forces. We haven't looked at that. We're going to look at it next chapter. But we dealt in, I guess it is fair to say we dealt with it when we were talking about the aqueous solution, right? Not just any liquid, but mainly water, because that is the predominant, solvent that we use in general chemistry, all right, in contrast to organic chemistry. Now, then we have solid and gases. So what is happening here, you see, in case of the gas fill up their container. And that is because of the freedom of movement that gas particle has. For that reason, when they expand, all right, beyond the size of gas particle, what happened, therefore, you can compress them, compress the space between the gas particles. And as you understand, when something disperses or expand in that sense, because there would be less particle in that particular area, that create a low density, because density is defined by mass for volume, and you are reducing the mass by further expansion or dispersion. So this motion, this gas being in a container and moving around, right? It has some freedom of motion. And when they move around, they bump, right? They bump each other, they bump a container, and that creates what we call basically a pressure, right? And then again, don't forget the fact that this distance here is much further than what you see. This is not the real picture. The distance is much greater. So in that scenario, when we're talking about the gases, it's important to understand that the volume is the volume of the dispersion, not the volume of the gases itself. So we could have a CO2, we could have a H2, which are different gases, right? And then for a CO2, which made of carbon, oxygen, and we understand the atomic size, it's very much different than the size of the H2 molecule, which is relatively very small. But that doesn't make any difference on the volume when we're talking about the gases as whole. Now we're going to talk about that later on, and when we are discussing molar volume. So the fact we can compress gases is because of the distance or the volume that gases contains due to the what, dispersion. Now we're discussing these gases can move around, have a freedom of motion that creates pressure. But to understand the pressure, this is how we define the pressure, force per area. All right. And we have different units for the pressure. You see here, Pascal, bar, right, or kilopascal. Now, this is interesting again. We refer to this average speed, not just a speed, average speed, because we are implying that the particle here, they don't have all of them same speed, some slower, some faster. So that's why we're saying average speed. So how we measure the atmospheric pressure, all right? We have air, and these airs, they have some pressure. Like any other gases, right? They have some pressure. To measure that pressure, actually this was covered by the person named Torricelli, all right, Italian fellow. And they fill up this container all the way to the top with what? Mercury. And this mercury is been inverted into this mercury dish. This is mercury here, it is the mercury. And then as they inverted, some mercury dropped to this level. Now this experiment was carried out initially at sea level. So at sea level, it's not high altitude or low altitude, it's right at sea level. They measured the distance, the mercury here from there, all right? And this distance found to be what, 760 millimeter of mercury. All right, so that would be 760 millimeter of mercury. The fact that this comes down is the gravity, right? Gravity pulled this down. Now, the fact that it doesn't come all the way down is because of atmospheric pressure. So atmospheric pressure, all right, atmospheric pressure, insert the pressure right here. This pressure prevents the mercury from what? Coming down all the way. And later on, 760 millimeter mercury equals 760 torr in the honor of Torricelli, right? So these are the same thing, basically. Millimeter mercury, okay? By the way, they call this device barometer. Another picture also showing it here. Now, 760 torr or millimeter mercury is equal to one atmosphere. So we use the unit sometimes for calculation. We use the atmosphere unit is 1 ATM, stands for atmosphere. So is equal 760 millimeter mercury or 760 what? Torr. Okay. Now we have also manometer used to measure the difference in pressure between atmospheric pressure and that of gas in the vessel. So you have the gas here, right? And this pressure here caused, this is also mercury in there, moving this mercury in this arm go higher compared to the other one. And this is purely because of what? Pressure inside the container. So the gas pressure is equal to the what? Atmospheric pressure plus this height. Because you have this is open, remember this is open right here. So if it is open, atmospheric pressure, what? Creating one atmosphere, and then this gas pressure has to what? Oppose that. And then to calculate the gas pressure, you take this height difference plus what? The atmospheric pressure, whatever the atmospheric pressure. The reason we keep saying atmospheric pressure right now here, because you got to imagine if this experiment was carried on, at the sea level, you expect to be what? Same 760, but sometimes the pressure is not 760. As higher altitude, the pressure drops. So it would be less than 1 atmosphere or less than 760 millimeter mercury. Okay. Again, they look at the device here. Manometer. Remember, this is open, right? So the gas pressure pushed this down, into the other arm. And the gas pressure is equal to atmospheric pressure plus what? The height difference. All right. Now see if you can answer this question. What happens to the height of the column of mercury in what? Barometer. Yeah, barometer as you climb to the top of the mountain. So you go top of the mountain, what happened to the mercury barometer? So what is the mercury barometer, right? That's the manometer. This one is what? Barometer. So it's asking what's happened. What do you think most likely going to be the scenario as you go top of the mountain? All right.
Number 2.
Right, is number 2. The height of the column decrease, right? The height decreases because the pressure decreases with the altitude. So you have less than 1 atmosphere as you go to higher elevation, right? So there are less force to hold the mercury up in the column, therefore is what drops. Any question there? No? No. All right. Standard pressure, right, is equal to what? Atmosphere, 760 millimeter mercury, and that is 101.325 kilopascal. And 1 atmosphere is equal to 14.7 pounds per square psi. Now, these are the simple conversion. All right. What is the pressure in millimeter mercury here? It's a simple conversion, yes. You got to do it from psi to atmosphere. Unless you have a conversion, then it would be, you can do it in one shot. But if you don't, then you have to take it one at a time. And first convert it to atmosphere, and then from atmosphere to millimeter mercury. You shouldn't have any problem with this type of conversion by now. Hopefully not, right? Another one. Now here going to from psi to what? Kilopascal. Again, you need to convert first to atmosphere and then from atmosphere to kilopascal. You got to look at the relating statement, and by relating statement means you have to have the conversion factor. So if you don't know those conversion factor, you never be able to do that, as I've been saying that. Now, if you know him, it's a matter of put them in there. You always put the in a manner that cancel out the units, all right? And then you get the unit that you desire. In this case, it's kilopascal. Now, dealing with the gas law, we're dealing with 4 variables. So to understand these 4 variables, we have temperature, pressure, volume, number of moles, right? Pressure, volume, number of moles. So we say here we examine several gas laws which are empirical relationship among these 4 variables, right? These 4 variables, they are related to each other. Let's see how they are related to each other. To define that, first, let's talk about standard condition. Standard condition is standard temperature and standard what? Pressure. Temperature of what? 0 Celsius, pressure of 1 atmosphere. So 0 and 1, standard temperature and pressure. Okay. And that's what the STP stands for. Now, let's look at a couple of things I didn't mention. I didn't mention is 273 Kelvin. Why? Because 0 Celsius is equal to what? 273 Kelvin. And also didn't mention standard volume. What does the standard volume means? All right, this is something that we're going to look into it, you know. As I mentioned, when we're talking about the volume of gases, due to the fact that there is higher dispersion, all right, due to the fact that the gas particles, they are so small, it won't make any difference what gas we're talking about. Whether we're talking about H2 or CO2, we can apply the same volume, which is what? 2 plus 2 gives you 4, 22.4 liter. That's a standard volume or a standard molar volume, because you need to define this volume is just for 1 mole. At the standard condition, 1 mole. From 1 mole of any gas at standard condition has the volume of what? 22.4 liter. Whether we have helium, carbon dioxide, carbon monoxide, methane, all right, CL2, F2, doesn't matter. They all have 22.4 liter, okay? Boyle's law. Boyle's law, what are we relating to each other? You look at here, you said the volume of a fixed quantity of the gas at constant pressure is inversely proportional to its pressure. This is a relatively easy concept to understand, that, you know, the volume of a gas is inversely proportional to pressure. So to show this mathematically, this is what we're showing. Right, the volume is inversely proportional to that. So what happens if the volume goes up, all right, then change in pressure is going to happen. It will be opposite, and vice versa. So when you put more pressure on something, all right, you cause into the volume to reduce. And you can see from this experiment showing here, right? Boyle's experiment. Now you see, you add in like here more liquid to here, and that caused more pressure. Now this happened, right? The volume changes. So to show this formula, right, we say P1, E1 is equal P2, V2. 1 stands for initial 2 stands for final. And as I said many times, in the cases like this, it doesn't matter. P initial, V initial is equal to what? P final, V final. You look at here, all right. Let's see the application. Look at the problem here. A cylinder with a movable piston has a volume of 7.25 liter at 4.52 atmosphere. What is the volume at 1.21 atmosphere? So it again doesn't matter which one you set up, P1, V1, or P2, V2, doesn't matter, you know. In that sense, whichever you do, mathematically you end up having it. But it's easier now to put the 1 for the one that is given first and then 2 for the later on. Or you can use, you know, initial and final with the I and F subscript. That would be fine as well too. So that if that makes it easier for you. Right, you solve the equation for what? V2. Very easy, right? The unit should nicely cancel out and you get the desired unit. Another problem. Now the pressure going from what? 782 to what? Atmosphere. Now you notice that the unit here is what? Not same. So you have the unit conversion prior to that. And also you look at the volume here. Volume is given what? In milliliter. Solving it for V1, right? Now this is what used to change the torr to atmosphere. And the volume comes out in milliliters. So we got to be careful what they're asking. Questions sometimes ask the volume in liter. You have to make a conversion. But if don't, then leave it as it is. Now next to Boyle's law, which was relationship between what? Pressure and volume. Now we're talking about the Charles law. What we're saying about the Charles law. So the relationship between a volume, now temperature. This one, it says what is directly proportional. So which means, you know, as you increase the what? Temperature, you expect the volume to increase as well. Okay. Now, since we deal with the volume, you got to be very careful here and understand most cases like that. We have to convert things to what? To Kelvin, because Celsius and Fahrenheit, as you may know, you have negative temperature. So the whole entire calculation is going to be based on something that it gives you negative what? Temperature and pressure. And that scale is, it would make the volume to be what? Negative as well, which we know something that doesn't make sense right here. So whenever you see the temperature in the problems like that, dealing with Charles' law, what do you need to do? Just add 273 quickly, convert it from Celsius to what? Kelvin. All right. Now the gas has a volume of, this is here, what is liter, right? At 0 Celsius. What was the temperature at 2.8 liter? Okay. So calculating for T1. Now, again, you got to convert the temperature to what? Kelvin here. Yeah. Then the rest should be easy.
Professor, I have a question.
Yes, go ahead.
When we convert to Kelvin, you prefer to use us 273 or 273.15?
Most of the calculations shouldn't matter, but do 273.15.
Mm-hmm. Okay.
Yeah, that's more precise, right?
Okay, thank you.
Because within that range, 273.15 Kelvin to find the equivalent to Celsius, it won't make much difference sometimes, right?
Mhm.
It seems a lot, 0.55, but not in scale of what? Celsius. Very little. And sometimes is that beyond because we don't measure the temperature with Kelvin. We measure the temperature with what? Celsius, mainly Celsius thermometer or Celsius devices. Of course, there are some digital equipment that they use Kelvin, but we do Celsius. And when you do Celsius, what number can you read? Basically, it's very hard to read on those thermometer. Many of them alcohol, or they used to be mercury thermometer, and 20.50. I mean, that's a significant. You get that, and in that sense, you're talking about 0.15 of Kelvin. Then that would be converted to Celsius, not much of a difference. But it's good question, I guess. You should use 273.15. Okay, this one is also easy. It's just algebra, calculating V2, right? You see that? And then converting the temperature to Kelvin for what? T1 and T2, because you're calculating V2. All right. Any question? Okay. Now let's look at another law. We talk about Boyle's law, Charles' law, now Avogadro's law. Case of Avogadro's law, all right, we're talking about the volume and relationship to number of moles. That should be very obvious, right? You have more of any gas, you expect to have what? Greater volume. So the relationship between a volume and moles, it has to be directly proportional, right? You have more of something, you obviously have larger volume. Now, in this slide, if you notice here, right? If you notice everything here, everything is expressed at STP, standard temperature and pressure. First, you see the molar volume. Interesting. We just mentioned that 1 mole of any compound, right? You have about 22.4 liter. So same here, here, here. And it doesn't matter what their size is, because we said at the very beginning, when we deal with gases, we are when talking about the volume, we're not talking about the volume of the gas according to their size. We're talking about the volume of the container, volume of the dispersion of the gas into the container. Now, obviously, they will have different mass for 1 mole of that compound, right? 1 mole of helium, it would be 4 grams, right? And then 1 mole of nitrogen, right, consists of 2 nitrogen atom, 14, 2 times 14, that's 28. And same goes for the what? Methane here with carbon and for hydrogen. And again, having a 1 mole, you have a fixed number of Avogadros, right? Like having 1 dozen, always 12, 1 mole, always 6.02 times 10 to the power of 23, Avogadro's number. And here you see the only difference is going to be what?
Mass.
Masses, right? Very good. Masses is different. So the mass is different because when we say 1 mole of helium, 1 mole of methane, they will have, but their volume They always stay the same, right? And it's interesting, we just said, the volume of the container, this depends on what? They have a relationship, right, to what? N, which is number of moles. So in each of cases here, you're referring to 1 mole. That's why they have the same volume. Yeah. Right. Okay, back to Avogadro's law. That is the formula we postulated by examining the fact that the volume and the moles, their relationship, they're directly proportional. To make them equal, you have to introduce the constant. And that constant means what? Volume over the moles is always a constant number, right? So V1 over N1 is constant, V2 over N2 is constant, which are both equal to each other. V1, V2, right? I'm sorry, V1, N1, V2, N2. Again, doesn't matter which one you call in 1 or 2, whichever is easier for you, that's fine. Now here in this problem, it's going to ask you how many moles, right? So you're calculating N2 here, in this case. Now we gotta be careful with this problem, because the problem sometimes, especially when you deal with multiple choice problem, when you read this problem, it says so many moles of sample of helium has this volume. How many moles must be added to given to that volume? It is true we are looking for N2 or the whatever final moles, right? But the question is not asking about that. The question is asking how many moles must be added. So if it must be added, you originally have some number of moles. How many moles were added? Once you calculate the N2, you need to subtract N2 from N1 to give you number of moles that is going to be added. So it is important when you read the problem to pay attention to these details. Okay. Now you see here, we find what the N2 is, right? And then we have to subtract it because we want to find out how many moles were added. Another problem, right? Calculating for V2, right? That's it. Easy, right? Okay. Now, a couple of things, when you look at this ideal gas law, right? Before we get into the ideal gas law, we were just saying like some relationship with the Boyle's law, Charles' law, and Avogadro's law. There are two ways to look at it. Either look at this in terms of the relationship, so you create what we call it ideal gas law, or we can combine this, make a combined gas law. Right? Yeah. So you can combine it like that. And what's the advantage of this? So if you have this right here, all right, you given any problem, any of these problems we mentioned earlier, given to you, and you have this formula, you can use it, right, to solve it. So in case of if the variable is not mentioned, just dealing with the pressure and volume, so you just scratch this off, cancel out, and look at that. If, for example, pressure and temperature is constant, you leave it like that, V1 over N1, V2, that is what Avogadro's law. You see that? So combined gas law can be used, to calculate anything dealing with these different laws here, right? And there is another way looking at them, how to combine them. Combine what? Combine their relationship. You look at here their relationship, how volume and pressure inversely proportional, and volume and temperature directly proportional, volume and number of moles directly proportional. You combine these relationships. You combine them to form what? This. You could say that volume, all right, is proportional to what? NT over P. Remember, these are postulated from right here, the relationship. We already worked that out. Now, we take that relationship. This is a proportionality constant. We convert that to what? Equation by introducing a constant. And that constant would be what? This is the very typical constant, gas constant that is used and universally accepted, all right? The trick about R is comes with different units. So you see all these variable units is being used, all right? But the one we're gonna be using for most of the calculation is gonna be this one, which means what? R constant is gonna be what? Liter atmosphere over what? Moles Kelvin. Now, since you know the constant, right? To go from proportionality to equation, we introduce R constant here. So that formula becomes that. And if we rearrange that, everything, we come up with what? PV is equal nRT, which is the ideal gas. All right, folks, you don't need to memorize or, repeat this, what I just said. I just explained to you how the equation were postulated. Now, it's up to you as far as whether you want to pay any attention to this, what I just said. But this is the formula for what? Ideal gas law, and that's what we use for the calculation. Now, you're looking at the constant, something very interesting about this constant, because if this constant were given to you, if I give you this right here, all right, then you can assume this is what? This is the value for the R right here. R is equal to, look at this, pressure would be P, L stand for what? Volume, moles stand for what? N, and the K stand for what? Temperature. So you literally can get the formula for the ideal gas law. This is going to be same from this what? Constant. All right, let's see. Let's do some problem here. How many moles of gas are in the basketball with total pressure of 24.3 psi? See, psi is not a very scientific pressure that we deal with in the lab. We normally like things to be in what? Either in torr or what? Atmosphere. Now, in the case that we know what we're going to do because we are using an ideal gas law. Now, look at this problem. The difference between an ideal gas law problem and the problems from Boyle's law, Charles' law, things like that. In all those cases, we had certain condition and we changed one variable and something else changed. But here, when you read the problem, all right, you don't see that change. You don't see that initial and final stage. You don't see V1, V2, you don't see that. So that's why you know that you have to use what? Ideal gas law. And in order to use the ideal gas law, you write the formula down, you see what variable you have and what variables are missing. Obviously, you should pay very good attention to what? Units. Because you're going to be dealing with what? R, which is what? Gas constant. For that gas constant, we want all of pressure to be in atmosphere, all the volume in liter, moles, of course, no unit there, and Kelvin would be the temperature. It's given in Celsius, so you know right away you need to convert the temperature from Celsius to what? Kelvin. And the pressure, same, you got to convert it from PSI to what? Atmosphere. So you got to do these two conversions before you do anything else. The rest will be very easy because you use the formula, put everything into the formula and solve for unknown. Looks like a nice algebra work, right? Okay. All right. Let's go. How about this one? Again, you have PSI, all right? And you have Celsius. So there are two conversions you got to be doing here again. Yeah. Now, this look at the two parts of this problem. You know, there are a couple of ways you can do that, all right? One way is, you know, doing it the way it describes here, all right? And if you do it any other way, it's fine. You know, they all will be the same. It says a gas occupies so many liters at that pressure and temperature. What volume will it occupy at what standard condition? Now here you need to find out what the number of moles in the first scenario, then take these to find out related to the SCP. Now, as I said, there are a couple of ways you can do that. Let's just do it this way. Find the volume, right? I mean, find the moles, and then put it in the next one to find the what volume. We should do the what routine conversion. Make sure we have the, because we are using this, then we need to have what? Pressure in atmosphere and the temperature in Kelvin. Now you put in this formula to find the number of moles, right? You can take this number of moles, as I said, put it in this formula to find the volume, or you can use molar volume conversion. What's a molar volume conversion? 1 mole of any gas is what? 22.4 liters. Remember? This is 1 mole of any gas. It gives us what? 22.4 liters of that gas. You can either use that, or you can use the what entire formula for what? Ideal gas law. So you get the same answer ultimately. So you got the volume here, right? Okay. All right. Now let's make this a little bit interesting, because when we deal with ideal gas law, we always mention moles. Let's not mention moles. We can mention what? Grams. So how does this work? It's easy, because we can always go from grams to moles using what? Molar mass conversion. Let's look at it. Now, as I said, here in this case, you've been given what? The grams of SO2. Of course, you've been given a formula, otherwise you won't be able to find the what? Moles. So you go from grams to moles using what? Molar mass conversion. And from that point on, is everything easy, because you solving ideal gas law for what? Volume, right? That's a molar mass conversion. And obviously you have to do the usual conversion of the units. In this case, you're going from millimeter mercury, right, to atmosphere. Why? Because of our constant. Remember, constant is given in that. All right. Now let's look at the other application of the ideal gas law equation. So one of them is density, right? Then again, we use the ideal gas law in the stoichiometry calculation as well in chemical reactions. So let's look at both of them. First, when we're talking about the densities and of gases right here, so the relationship PV is equal nRT can be rewritten like this. Yeah. You just move things around, right? And then we look at that relationship, right? We understand that we say moles times molecular mass, it gives you what? The mass of compound. This is really molar mass definition. So it doesn't matter how you put this here. Because, when you're talking about the molar mass, right? When you talk about the molar mass is equal to what? Mass typically, right? Grams, we say mass, grams, doesn't matter, per mole, right? N, yeah, that's what molar mass is. So you rearrange that, that's what you get. All right, yeah, okay. Let's look at this, right? Rearrange that. You can rearrange it to get that. Again, you don't need to memorize this. This is just to show you how we arrive to certain equations. And we use this relationship, all right? And we multiply both sides by what? Molar mass M or Mn, it doesn't matter, same thing. And that's what we get, right? And if we get that, we can write it like this, okay? Because it's M over N, yeah, multiply that, that's what you get. Once you get that, that can be also rearrange it to write it like that. So this is the density. Density, we know density is equal mass over the volume, right? We learned that from what, chapter 1 or 2. Now we introduce in another here, PM over RT. This M is a molar mass. Now you pay good attention. This M is a molar mass here. And this is the pressure, temperature, and R constant. All right. So that's the formula, or you can write it like that. To be more specific, molar mass is equal to what? Density times R, gas constant, T, temperature over pressure. All right, calculating the density of N2 at STP. How do we do that? What do we have? By looking at N2, you know for sure you have what? Grams, correct? You understand that. When N2 is given to you, you know, okay, I have N2. What is the mass of it? It's just 14 grams, right? And then this is the volume. The volume is volume of what? This volume of molar volume at STP. Remember I said 22.4? It's always 22.4, right? It says calculate the density of N2. Obviously, you see N2, you just don't see one mole. 1 mole of N2 at STP. So what else we have at STP, guys? What does STP stands for? Standard what? Temperature and what? Pressure. And what's the temperature? What's the standard temperature?
273 Kelvin.
273 or 0 Celsius. And what's the standard pressure?
1 atmosphere.
1 atmosphere or 760 millimeter mercury or 760 millimeter torr. So you can use that, you know, and you understand that here you say mass density is simply this mass over the volume, right? You don't need to do that. You can use the other equation. Mass is what? Molar mass, and the volume is molar volume. If you're using a molar mass, then you're using a molar volume, right? That makes sense. And that's what you get. Any question on this? Now, this is not at STP. we got to do the conversion. And what conversion are they? Here, going from millimeter mercury to atmosphere, and going from what? Celsius to Kelvin. Is that right? That's what you guys got, or you didn't work it out? All right. Okay, let's do another one. Okay. Set things up. Find the volume. Then once you get the volume, you use the formula we mentioned earlier. What formula is that? Relationship between density and what? Mass volume to find the density. You've got to do the routine conversion, both for temperature and pressure. Use the ideal gas law to find the volume. Once you find the volume, then density is defined mass over the volume. That should be easy. All right. Any question? Oh. Okay. Okay, we find the N, number of moles. Then you use the equation for density. All right. Not density, I'm sorry, use the equation for molar mass. Yeah, you guys have, hopefully nobody has problem with this. You have problem with this right here? Because remember, the definition of the molar mass is what? Mass per 1 mole, and this is Mn, right? That's the definition of molar mass. Do the conversion, then find the number of moles. Now from that, you find about molar mass. Okay, that's close, right? It doesn't ask for the identity of the gas, just ask you which one it is. All right, what's the molar mass of the gas if 12 gram occupies so many liter at that pressure and temperature? All right, let's look at this problem. We use the ideal gas law to find number of moles. All right, and then we use the relationship to find what? Molar mass. Okay, any question here, folks? All right. So we're going to look into the gas mixture and partial pressure. I think probably this part you guys been covered that, and this is very easy. Dalton's law of partial pressure. It states that if we have the mixture of gases, partial pressure of all the gases, let's say we have hydrogen plus oxygen plus nitrogen plus ammonia, all right, is equal to what? Is equal to total pressure. It's very simple. You just add them up and that's what you get. in terms of partial pressure and mole fraction, there's a relationship here, and we're going to go over that. But you will see how mole reaction is related to partial pressure. Okay. This is Dalton's law of partial pressure, as we mentioned before. As you see, P1, P2, P3 stands for the individual partial pressure, so it doesn't matter which one designated 1, 2, 3, 4, 5. All right. And now when you look at the total pressure, bear in mind that if we mix some gases together, we understand the P total concept is clear from this statement and from the Dalton's, law of partial pressure. Now, if you think about the concept of temperature for this individual gases, they should all have the same temperature. What about the volume? Will the volume of this and the volume of this will be different, or all they're going to have the same volume? I'm asking, maybe somebody wants to answer that.
Would it be the same volume?
Yes, it would be the same volume. So when we look at the variables that we define gases, what are the variables? Remember, this pressure, volume, and then what? Moles.
The IT
Yeah.
temperature.
That's it. These are the variables, right? Of course, R is constant. We don't say variable because it's constant. But pressure, volume, moles, and temperature here. I think I mentioned the volume one more time here. All right. Now you see these two, how they are the same for all these individual gases. What about the N? Can we say the same thing about the N?
No, N is different.
And N is different. So it is fair to say that for N, we also have N total is equal N. It doesn't matter how you set it up. You can set it up N A, B, C, or just put simply N1 plus N2 plus N3, which is 1, 2, 3 stands for the individual gas. And if you look at the ideal gas equation, if you were to write the ideal gas equation for this, considering what we just said, you can say that pressure total, right, relationship, because we have a PV, is equal N total RT. You see where I'm getting that? This would be for a total. Okay. Now for the individual gases, obviously we have to find the partial pressure of A. Let's say A is the oxygen here in this case, and this is nitrogen. You have to use the pressure of nitrogen and moles of nitrogen if you're working out for that individual gases. But when we're talking about the total, right, then you should use this formula with the P, understanding P and N, which is pressure total and moles total, is the sum of moles and pressure of individual gases. Okay. Let's look at some problem in the same context, whether we can do it or not. Determine the mass of argon gas in a mixture of gases with the following information. So here you understand they're asking about the mass in gram. Let's see what information we have here. We have both pressure and we have total pressure, okay? Then we have both volume and temperature. Remember, volume and temperature, right, is same for all the gases regardless. So what exactly they're asking us here to find out is a mass of argon. We look at this problem. If you look at the problem, we understand that variables used for ideal gas law, there is no mass in gram. However, we have what? Moles, right? This is the ideal gas law. PV is equal nRT. You see, we have moles here. And if we have moles, we can convert the moles to gram using what? Molar mass. Now, the question is, since we are focusing on argon, do we have moles of argon here in this problem?
No.
No. Huh?
No, we don't.
We don't have a moles of argons, right? So what do we have? We can get that. What do we have here? Do we have the pressure of argon? Do we have pressure here?
We have total, but not the pressure of argon.
Okay, so which means we can determine the what? We can determine the pressure of argons, right?
Mm.
Okay, if we get the pressure of the argons, then can we calculate the moles then?
Yes.
All right, let's look at it. Now, as far as conceptual plan is clear what we are doing, right?
Mm-hmm.
From Dalton gas law, here we are determining the partial pressure of argon by subtracting the individual partial pressure from total pressure, right? You get argon here. Once you find the argon, then, you know, you put it in the ideal gas law equation, find the moles of argons. Then from moles, you convert it to mass using what? Molar mass. So Dalton's ideal gas law, molar mass. And the rest is just a matter of calculations, right? Now you got to be careful to have everything in the desirable unit, because that may cause problem if you do not do the conversion. Remember, our conversion should be based on what we have, and what we have is what? Our universal constant, which the unit is in atmosphere liter mole Kelvin. So obviously what we have in millimeter mercury, we need to convert it to atmosphere, right? This is a conversion factor. And then we put it in a formula and we calculate the moles using ideal gas law. Now, once you get the moles, convert the moles to gram using molar mass of argon. There it goes, you have in grams. Any question? All right, let's do another problem. Now, this problem is a little bit different, right? We're asking, find the partial pressure of neon in a mixture with the total pressure of 3.9 atmosphere. So we want to find the partial pressure of one of the gases, and the total pressure is what? 3.9. The volume is given to you, the temperature is given to you, and the moles of xenon is being given to you, right? So how do we go about this finding it?
We need to find pressure, partial pressure of xenon.
Right. Right.
And then from total pressure, we find the partial pressure of neon.
Yes, it's very easy, right?
Mm.
For this problem, it's fairly easy. Here, from the ideal gas law, we find the partial pressure of xenon. We understand our two gases mixes together. All right, you subtract this from the total, that give you what? Neon partial pressure. Right? The one before was a little bit more complicated, but this is easier. Very similar in a sense. But you have conversion there, another conversion, because that conversion involved what? Going from moles to grams. That's a molar mass. Obviously, we already covered that in earlier chapters. Okay. Any question here? Okay. Now let's talk about the mole fraction. Mole fraction. What is mole fraction? Now you see the mole fraction. When we say fraction in principle, we are taking things to be in unity of one, right? When it's a mole fraction, it's a fraction of what? One. So when you have a mole fraction, we're talking about total has to be one. Is like saying percentage, right? The total has to be what? In percentage. It has to be what? 100, right? So in mole fraction, all right, the total has to be what? One. That's the difference. So to get the mole fraction here, we can say is what? Part per total, because that gives us fraction. Remember, if I parts per total times 100, then that would be what? Percentage. So percentage is a fraction times what? 100, basically. Or part per billion is what? Fraction times a billion. That's how it goes. Now, if you look at this, mole fraction is equal to that, and also this is equal to that. So this is also make it to what? Equal to the mole fraction. This is a symbol for individual gases right here. A, for example, could be oxygen, could be whatever. But total is total, like you understood that. Now, if you have the mole fraction of A and mole fraction of B, so you have X of A plus X of B, this has to be what? Equal to 1. That's what I was saying, right? And usually they show the symbol like this. Now, this is fairly easy formula here. If you pay attention, partial pressure per total pressure, partial mole per total mole, or per mole of A over the total mole, that would be same thing as calculating what? Calculating mole fraction for both. So it doesn't matter which one we use. We can use the pressure, we can use the volume, we will get the same exact answer. Now, something interesting here is this. We are saying partial pressure of A, all right, is equal. How did we arrive this? Where we get this from? We get this from this relationship, right? From this relationship. So if you do cross multiplication, that's what it means. Let's say the total pressure is 10 atmosphere. And mole fraction, you can use any fraction. Let's say is what? Half, right? Remember, half and half is equal to 1. Let's say it's half. So if it is half, then the pressure would be what? 10 times half, that gives you what, guys?
5.
5. Does that make sense? So you see how multiplying total pressure by fraction, because you have 10, you multiply it by the fraction, it makes it a smaller number, right? In a sense, that would be the partial pressure. Okay, I'm just playing with your mind, scratching your head here about this, you know. Let's do some problem, we understand things better. Find a mole fraction and partial pressure in a 12.5 liter tank. So as you know, when you have a mixture of gases, right? You put it in a container, it doesn't matter, they take up the whole container. And that's 12.5 liter. With so many grams of helium and so many grams of oxygen at that temperature. Now what we're trying to find out, we have both grams, right? We're trying to find a mole fraction and partial pressure of oxygen and helium. How can we do that?
We need moles.
We need moles, very good. So that means we need to convert those grams to moles. If we convert them to moles, then we can use the formula that what? Mole fraction is equal what? Individual mole over what? Total mole. Because if we have both gases, grams, we can find the moles. If we can find the moles, that means we can find what? The mole fraction of each one of them. All right, I will show you this because maybe a little bit more challenging. Now we have mass in grams. We convert the mass to what? Moles. And we go from moles to what? Mole fraction. I remind you about this relationship. Remember, we had this X of A is equal to what? N of A is N total. You recall this formula, right, guys? That's what mole fraction. So when we go from here to there, this is what we need to use. Okay, so we'll be clear here. And once you get the total moles, we can find the total pressure using what? Ideal gas. So very first step, we get the mole fraction, we find about total. Oh, yeah. Now, if you have the P total and you have what? P total and mole fraction, remember, if you multiply that, then you get the partial pressure. We just went over it, right? 10, I gave you an example of 10 multiplied by mole fraction half. I think it was Thaler was set 5, right? Remember? Okay. So we can find the pressure of individual gases using, well, this relationship, mole fraction and total pressure. Okay, let's do the problem. First of all, we need molar mass of helium and molar mass of oxygen. Okay. And this is the conversion from what? Grams to mole using molar mass for helium. Molar mass, right? You get that from periodic table, folks. Formula and periodic table. Same for oxygen. You should know this by now. You have moles of individual gases. Now, what do we need to do? We can add them up to get a total mole. Once we add it up, we get a total mole, then we can find about mole fraction of each one of them. Right? So you see mole fraction of helium is a moles of helium over what? Total. These total right here. Same goes for what? Oxygen. You do the same thing with oxygen. Moles of oxygen divided by what? Total moles. These are the same thing, total moles here. And you see, if you add this up, you should get what? You should get, technically, you should get 1. Now you got the mole fraction, right? And then total mole. We use the total to find about pressure here. Now that would be total pressure. So we have the mole fraction, we have a total pressure, easy. In each cases, you multiply what? Total pressure by mole fraction, sorry, that gives you what? Partial pressure of helium. And let's do the same thing for oxygen. All right, let's look at another problem. Find the mole fraction of neon in a mixture with total pressure of 3.9 atmosphere. Volume is 8.7 liter, temperature is dead. And that gives us also 0.17 moles of what? Xenon. Break it down for you. So here we have the mole of xenon, I'm sorry. We can find the partial pressure of xenon. Yes? You look at the total pressure is given to you, all right? And what else is given to you here? The volume, temperature, and the moles of xenon. So from having a moles, volume, temperature, we can find about partial pressure of xenon. Once you get a partial pressure of the xenon, you subtract that from total pressure, that gives you partial pressure of what? Neon. Now you have the partial pressure of the neon. You have a partial pressure of the xenon. What can you do? You can find out about mole fraction, right? It's very easy because we said it at the very beginning. Mole fraction, for example, this is neon, right? Mole fraction of neon, it could be equal to the moles of neon over what? Total. Or also you can use what? Partial pressure of the neon over what? Total pressure. So here in this case, we're using this. Now here, you can see this is the ideal gas law. This is the Dalton's law. And this is, again, mole fraction. First, we find the pressure of xenon. Then we subtract from total to get the pressure of neon. Then we simply say partial pressure over total pressure. That gives you what? Mole fraction of neon. I recommend you take this problem and just don't look at the solution, try to do it yourself. Because problems like this, it's nothing can change really. The whole thing is just right there. You can have different gases, a little bit wording different, Other than that, the calculation is exactly the same. Okay? Now, I believe majority of you been in the lab, or at least majority of the people here been in the lab and paying attention to what's going on. And you realize that our reaction in the lab is carried out using water. When you have water, what happens? The individual molecules of water escapes the surface and they become part of the gas collection, all right, in the various experiments. So when they become part of the gas collection, then you're not dealing only with one gas. Now we are dealing with the mixture of gases. So you should apply law of Dalton's law of partial pressure to those as well. So you will going to have a total pressure, which one of the partial pressure obviously is going to be what? Water vapor. Now, in this case, you see zinc reacting with hydrochloric acid, forming H2 according to the metal activity series that you learned in earlier chapter. The hydrogen is formed through the redox reaction or simple displacement here. And you will see that the individual hydrogen molecules, right, is mixed with what? Water molecule. These are white, stands for just hydrogen, and these red one, because oxygen usually is displayed red, that's why it is like this: oxygen and hydrogen. Hydrogen are white, oxygen is red. That's what you see here. All right. Now, so what we need to do, we need to apply this in calculation. For example, look at this problem. So many liters of oxygen collected over the water at that temperature with this pressure. Find the mass of oxygen. Now, this is, look at this, this is very interesting, you know, because a problem like that, you know, is given you find the mass of oxygen. So how can we find the mass of oxygen? What do we have here? We have the total pressure, right? We have the total pressure. And then what else we have? We have temperature, right? And we have what? Volume of oxygen. So there is something here missing. What is that? Since we are using water vapor, the total pressure should equal to what? The pressure of oxygen in this case, plus what? Water vapor pressure. Now, we don't have the water vapor pressure, but we can always look up the water vapor pressure. In the lab, for your lab, you saw the very last page, I believe. There's a table with the water vapor pressure in that table. Obviously, if you Google water vapor pressure, you can find the water vapor pressure at different what? Temperature. So you need to have the temperature in order to look up the what? Water vapor pressure. Here, temperature is being given. So since you have the temperature, you can refer to your textbook or simply Google and find what? The water vapor pressure at, the vapor pressure of water at that particular temperature. All right. So here we go. We need to what? Find vapor pressure of water, so we can subtract from total pressure and then get the pressure, partial pressure of oxygen. To do so, we need to look it up. And once we get what? Partial pressure of oxygen, we can use what? Ideal gas law, PV is equal nRT. Write it down, kind of, you forget maybe, right? To use that to calculate what? Moles, which is moles of what? Oxygen. Once you know the moles of oxygen, you can obviously go to gram using what? Molar mass. So here we go, Dalton's law of partial pressure, and look it up at water vapor pressure as 20 Celsius. Where we got the 20 Celsius from? 293. If you subtract this from 273, that gives you what? 20 Celsius. But it doesn't matter because some they have in Kelvin anyway. So we get this pressure from the table. So it's given to you. Now, during the exam, obviously, I have to provide you with that information. I'm not just going to leave it to you that you're going to Google it. So simply, I will offer you that information during the test. Okay, so no problem for that. Now, there is a matter of unit conversion. Why are we going from millimeter mercury to atmosphere? Because then again, we are dealing with what universal gas constant are, which in unit of what? Atmosphere liter mole Kelvin. So you got to be very careful with this. When you do problem like that, pay attention to units. Now, once you can determine the moles from here, find the moles, you get the mole, then the rest should be very easy to go from moles to grams using molar mass of oxygen. All right, let's go to the next problem. We have moles of hydrogen is collected over the water, right? And the volume, again, volume and temperature is same for both, remember? Always temperature and volume, two variable, it would be same for the mixture of gases. Find the total pressure. So if you got a total pressure, all right, so that means we are looking at collecting a hydrogen, all right, with collecting a little bit of water vapor. So when you say total pressure, they want the pressure of what? Pressure of hydrogen plus the pressure of what? Water vapor. So partial pressure of water plus partial pressure of hydrogen. So how do we go about finding the partial pressure of hydrogen? Can we find the partial pressure of the hydrogen here from information is given? Can we?
Yes.
Yeah, we can.
If you've done it right now, you see the water vapor pressure at 50 Celsius is what? 92.6. Yeah, go ahead, Tal.
I thought pressure was supposed to be in atmospheres.
If you have the water vapor pressure, right, in the, for calculation, you are using atmosphere, right? You're changing it because of most of the tabulated data are in millimeter mercury.
Okay, so if we have to use this like chart or online, it's going to be in
Yes.
your mercury. That's why we have to change it.
Yes, yes. Unless this has been given to you in atmosphere, then you use whatever you have, right?
Yes.
How about now we use ideal gas law in stoichiometry calculation? We understand the only relationship we have between, product, reactant, product in chemical reaction in the stoichiometry is always based on what we call it the molar ratio. And the molar ratio is nothing but coefficient on to the left side of the reactant and product in chemical reaction. To understand that, and the fact that ideal gas law, one of the variable is mole, so many times in chemical problem is given to you, they give you pressure, volume, temperature, and they expect you to find a mole of B, for example. So which means you have to have, first of all, a chemical reaction to find the molar ratio. Second, you need to calculate the moles of A from the chemical reaction and the formula that is given to you using ideal gas law. And once you find the moles of B, maybe they ask you for the volume or another information, so we can easily find it using what? Same ideal gas law. And for this type of stoichiometry, All right. You have to just be careful that you're going to need have a reaction. And for the reaction, don't forget, you need to have what coefficient to the left side of product and reactant so you can figure out the molar ratio. All right. There is one more emphasis here about STP, standard temperature and pressure. 1 mole is always 22.4 liter. I think by now you should know this. All right, let's look at this. What volume of hydrogen is needed to make so many grams of methanol at that pressure and temperature? Now you see what they're asking you here. Now is asking the volume of hydrogen is needed to make so many grams of methanol. You look at the chemical reaction here, they are giving you grams of product, right? They're giving you grams of product. And they're asking you what volume of this you need. That's what they're asking. So you see, for one of the product reactant is given grams, the other one asking for volume. If you are given this and they're asking you how many grams go from grams of this to moles of this would be easy for you. You say grams, convert them to moles, and moles go back to the moles of hydrogen using what? Molar ratio. Now the twist here, they're not asking about the moles, but they ask about the volume. But once you get the mole, having those information, what information is that? You look, you see the pressure and what? Temperature is given. If you have a pressure and temperature, and then you have what? Moles, you obviously you can find a volume using what? Ideal gas. Look at it. All right, you go grams to moles using what? Molar mass, right? Moles to moles using molar ratio. Then you use ideal gas law to find the volume. You see how we're going from grams to moles of what? Hydrogen. That is a stoichiometry. That's something you should have learned earlier. And then once you get the mole, you have to do the conversion here again, because the pressure is given in millimeter mercury and the constant is in atmosphere. So you put it in there. All right, perfect. Let's look at another problem. How many grams of water form when so many liter of hydrogen reacts completely with oxygen at STP? So you see nothing is given here, but the liter of what? Liter of what? Hydrogen. Why is that? Because it tells you at STP, and STP means what? Standard temperature and pressure. Temperature is what? Temperature is
Celsius.
0 Celsius, and the pressure is what?
1 atmosphere.
180.
Yes. All right. So you can find from going from the liter of hydrogen to find the moles of hydrogen. All right. And then you can do the molar ratio to find the moles of what? Water. Now, for first relationship, going from the volume to moles, we are going to use molar volume as conversion factor. Can we do that? Yeah, of course we can do that. We can use it like a density, right? Like a molarity. But here we define, right? 1 mole of any gas, all right, is going to be what? Have a volume of what? 22.4 liter at STP, right? And then molar ratio, obviously, you look at the chemical reaction, you get the molar ratio. Mole is 2 moles to 2 moles. And then going back from moles to gram, you use what? molar mass conversion. This is a molar mass. This is a molar ratio. This is a molar volume, MV. That's what your experiment is all about, right? Molar volume of hydrogen gas. So you should get that answer, 22.4 liter. Okay. Very easy, very nice. Molar volume conversion, molar ratio conversion, molar mass conversion. You set it up very nicely and everything is going to work out. Anybody has any question on this? All right. So this is a chemical equation is given. Molar mass is given. So everything should be fairly easy here, right? In this case, if you have a pressure and temperature, it's easy to calculate the rest because you need only the moles, right? All right. Now, if you have the gram of mercury oxide per chemical equation, you can go grams to moles, moles to moles using molar ratio to find the moles of oxygen. Because if you have a moles, you have a pressure, you have a temperature, then you can calculate what, using ideal gas law to find what the volume is. And that's what we are doing. So we find a mole of oxygen from what? Grams of mercury oxide. You have the grams of this. You go from this grams, convert it to what? To moles. From the moles to what? Moles of what? Oxygen. This relationship based on chemical reaction and molar ratio. Okay. Now you see very nicely molar mass here, right? Grams to moles, molar ratio here, ideal gas law. So we set it up to find the moles of oxygen, and then rest is going to go using ideal gas law to find what? Volume of oxygen. We're okay?
Yes.
All right, kinetic molecular theory. This concept is, again, something you should have partially at least covered in introductory chemistry, but is based on the very fact that, gas particles, they are flying around and causing a pressure, and the distance between the gas particle, they are so small comparing to the distance is so large comparing to the size of gas particle. Gases consist of a large number of molecules that are in continuous random motion, right? No attraction between a gas particle. That is, again, is the ideal behavior, that there is no attraction. But this is not true in certain circumstances. And this is not something for you to memorize, but in your textbook, it doesn't show how they drive that equation. So I just thought it would be nice for those of you who are interested to see that. This is based on the kinetic energy, remember, because these gas particles, they're continuous motion. And there is such a thing, I call it the RMS speed of gas particles, and that's how it's been calculated. Again, I don't want you to try to learn these steps, just how to arrive it. Don't worry about it, just use the formula. And as I mentioned, that kinetic energy of these molecules, they're directly proportional to what? Temperature, right? As you raise the temperature, the molecules, they're going to move faster, more kinetic energy, and so forth. And the relationship, again, shows this formula. So this is RMS speed, TRT. This R is different unit, all right? And this M is molar mass, right? See, the unit is different now. Okay, because you have joule mole and Kelvin. It's a molar mass. So the bottom line is that is the formula that you need to use for calculating RMS. This is the average velocity, right? Because of this gas motion that you have. Let's put it in a problem so you see that there are not so many different type of problems I can give this. I can give on this topic. It's very simple. Problem is very straightforward. I know the equation is something that you never done it, but if you have a formula, you should be able to put the information in there. Calculate the RMS velocity of oxygen at 25 Celsius. So problem like that, it should be very easy if you understand the formula, right? And the formula is what? RMS is equal to 3RT over mm, which is molar mass. Here we have the molar mass of oxygen. Because the formula is given, we can find the molar mass of oxygen. Now what else we have? We have a temperature. So we have a temperature here, R, which is the gas constant. As I said to you, you know, it's a different unit. You need to look it up, or you look through your notes, you know, if they have a calculation involved in that. All right. Now, be careful the temperature. Because of, again, using an R unit, you have to have a desirable unit as well in terms of temperature. All right. So you put it in a formula and you solve it, and here it goes. That's what you should come up with. Okay. Again, this is for methane. Very similar. RMS of that. Okay. You need to have a molar mass and you have to have temperature. This is a formula right there. Temperature, use Kelvin, put it there and solve it. That's it. Okay. The effusion and diffusion, this is again is very simple concept. You know, most of the times you may be wondering when you have a helium balloon, you come and you see what? The helium balloon is not floating anymore in your room and is coming down. So what is happening is basically the gas leaking. Because the gas molecules, they are very small. That's why due to this motion that they have, this movement they have moving around, and they get enough velocity and temperature to escape the membrane of balloon. All right. So that comes to the confusion of effusion and or diffusion. You need to have a very small hole that gas can, you know, escape. Now this rate of escape, the rate of how fast the gas go through this, it has something to do with what? With the molar mass of that gas. Now you see they're showing an example of argon and helium, how helium is staying here. Next day you come back and it's going to what? Coming back down. Now diffusion is also happen, diffusion always. The word diffusion basically meaning from something going from higher concentration to the lower concentration. All right, that could be through space, it could be through liquid. All right. That brings us what we call it, what Graham laws, effusion. It's saying that when we have two gas, right? We have two gas, right? Gas A, gas B, and we are mixture. You want to find out the rate of these things, you know, how they are effusing with respect to each other. You can set up the rate of A over rate of B, molar mass of B over molar mass of A. Okay. And in your text, this is all you have, rate of 1 or the rate of 2. You see that's a molar mass. This is kind of opposite, square root of that. Okay, let's see some of the application in solving problem. Calculate the molar mass of the gas that effuses at the rate 0.462 times N2. Apparently the gas is unknown, all right? But if you look at this formula is about the ratio of gas A and B, or so one of them to have to be unknown. It's no big deal, right? We still can set up the same thing, right? We say gas of unknown over to the nitrogen is what 0.462 times, because that's what it says, that relationship. Now, what are we looking for is to find the molar mass of the gas, whatever the gas is that, unknown is, right? Because we have the molar mass of nitrogen and we have this, right, information. So we can set it up very nicely. Here we have this, all right? And we have molar mass of gas A and B. And in this case, one is unknown. So we put the unknown there, right? We put the unknown there and try to solve it for unknown.
I'm a little confused with like rate gas A, rate gas B. I know it's like 0.462 is for nitrogen, but like I don't understand how it's unknown over nitrogen.
The gas that if used at the rate 0.462 times nitrogen, right? Why are you confused again? Because it says nitrogen here, right? You see that?
Yeah.
And it says at this rate. So the rate is what? The rate of unknown to nitrogen is 0.462.
Oh, okay. It's not saying the rate of one and then the rate of the other. It's giving you already what it equals.
Right.
Okay.
It says, it gives you the ratio basically, all right? But that's what you have. This is ratio, right?
Yes.
You understand? Right.
Yeah, I thought like that
No,
0.462 is supposed to be that bottom one, but I see that it's actually giving us what it is instead of giving us the
ratio. Yes. They're giving you a ratio. Then you see, it's simple, very simple actually. Yes, I understand how you got this confused, but it tells you what the ratio is. There it goes. All you have to do, put it there and calculate the what unknown molar mass, and that's what you come up with. Okay. Calculate the ratio of rate of diffusion for oxygen to hydrogen, right? If you're going to do the oxygen to hydrogen, this is equal to what? To what in reverse, right? Their molar mass is square root. Yeah? So you have the molar mass, right, of both of them. Now you find this, again, rate. You're not finding a rate of oxygen or hydrogen, you find a ratio here. This is a ratio. I need to remove that. This is correct. The other one was wrong. Just make a note of it, just in case. Ideal behavior. Okay. Now, ideal behavior, as I said, the gases at two scenarios, they no longer follow the ideal behavior, either at very cold temperature or at the very high pressure. Because something happened, at those two scenarios, all right, the ideal behavior is changing. All right. So we have, say, there is no attraction between the gas molecules. There is no attraction all the time. All right. Well, no. If we lower the temperature, we lower the temperature to such a cold temperature that kinetic energy slows down, motion is slowed, the gases is still attracting each other. So you feel a little bit of attraction. And if you feel that attraction is there, therefore the real pressure you expect to be what? Less than what? Ideal. Pressure goes down, right? Because they're attracting each other. Now, what happened, the gases typically, they do not take so much room, right? And we dismiss it. And when we calculate in a volume, we don't look at the volume of gases. We don't take it into account. But now, if we increase the pressure, the volume decreases. And we keep increasing the pressure, volume decreasing. So gas particle that they have this distance, now they have this distance and a smaller container. So in that scenario, the volume, all right, the real volume, you have to take into account the gas particles. So you expect the real volume increasing compared to the ideal volume. Okay. Now, if we are taking into account the gas size, right? And now we need to look at what we call it van der Waals equation. All right. This van der Waals equation is the information that correct the ideal behavior to have what real gases. Now you look at here, volume real is larger than volume ideal, and the pressure real is less than that because of what I just told you. Now for the volume, you understand now you have to take into account to make it larger, taking account that the size of the atomic size. This van der Waals information, van der Waals constant, is given to you, or it will be given to you during the test because these are constant and you can look things up online. Also for the pressure, the same way it has to be corrected according to what the moles and what A again is a van der Waals constant. So A and B both, they need to be what looked up if you are doing any calculation. So now this is what your book provided. This is general formula. Remember the formula is PV is equal nRT, which in this case, the P was corrected for van der Waals contribution, and the V, which is the volume, also was corrected for what? Van der Waals contribution. So you have look at the problem here. Is asking, using a real gas law, find the pressure of 2 moles of carbon dioxide at so and so temperature. The volume is given and the van der Waals information is given. So you are using a gas law right here to find a real gas law. If you do the real gas law, then you need to what? Have a van der Waals information. That means you need to have this constant. So how do we do this problem? I do it very simple and finish it, let you guys look at this. From this information, you can calculate the real pressure. All right. So that means you need to have an A and B van der Waals constant. And you can also, for the same information, calculate the ideal pressure using the formula PV is equal nRT. All right. Now for the real, you need to use this formula below here. Now all you have to do, put the information in there. This formula is this, and this one is this, and you come up with these two answers. As you see, the pressure, the real pressure is less than what? Ideal pressure, all right, because of what we told you that at lower temperature, you end up having a very low temperature, that is, you end up having less pressure and you deviating from the ideal behavior. Any question on this, guys? Okay. Perfect.